Welcome, I'm Al Fox and I'm chairing today's OI conference, Data Interpretation AI track. And the session is Machine Learning, Survey, Navigation and Simulation session. That's a bit of a mouthful. So today, my first speaker, I've got three talks, is Adrian Boyle. He's the CEO of the Cathix Group. Many people know Adrian and have used his products and services. He has a PhD in physics and he's always been interested in laser and optical systems. He has worked in Sweden, and most of us know him from his time in Ireland. He joined Machine Vision Technology in 1998, and since 2009, he founded Cathix Ocean. They're specialists in optical machine learning and automation, and many people know Adrian through the Cathix camera system, which has somewhat revolutionized how we do subsea and underwater inspection. So Adrian, over to you.
Thank you, Al. So I'm going to share my screen and hopefully that appears for everyone, and we'll go into presentation mode. So I hope everybody can see that.
Yep, we can see it.
Okay, so what I'm going to talk today about is robust real-time subsea machine vision, and with a focus on unmanned operations. So I'm also going to start my stopwatch because I've nobody to shout at me. Okay. In about 20 minutes time, I'm hoping, if you're listening to this, that you have a better sense of what Cathix have done in the last 4 years, but more importantly, what we're working on today, in part due to COVID, but also in response to climate change, and what we're planning to release in 2021, particularly for the purpose of deploying what we call fast digital inspection, as I'll refer to is what Cathix imaging systems do. I'll explain that, and I'll also explain what we're calling unmanned fast digital inspection, which is the transfer of that technology into the unmanned scenario. So very briefly, Cathix, we're based in Ireland. We started in 2009. Our operations are globally, and essentially we work in Gulf of Mexico, Australia, Aberdeen, and pretty much anywhere that there is AUVs or ROVs, we have systems deployed. Manufacturing and development is done in Ireland, and then our markets and the areas we work in are they range from oil and gas, defense, oceanographic, and if you go to our website, you'll see many of the different case studies where we cover things like sustainable fisheries, oceanographic research, and particularly with an impact assessment on the ocean environment. So there's projects from the Alfred Wegener Institute. You can read a little bit about them. I'm going to focus today on pipelines and a little bit about structures at the end, just to give a sense of what it is that Cathix systems do in the unmanned environment. So, and if you want to do some reading, we filed a bunch of patents in 2012 around all of the technologies that we described. They're in the public domain, and you can read them, but they're probably about 70 pages long. There's 6 of them, but they describe in quite a bit of detail what underlies what I'm talking about today, and you can read a little bit more about that. So, as I said, our focus since 2012, if you read those patents, you'll also realize the language we used then isn't the same language that's used today. There's different names for things. We've evolved technology, we've evolved the language, but it's in pretty basic terms in terms of augmentation, composite images, 3D models, and point cloud data sets. So to give an overview of our customers, they cover the broad spectrum of subsea contractors, oil and gas companies, a lot of AUV manufacturers. So we would have shipped maybe 30 to 40 systems to Kongsberg Maritime for AUV for both defense, oceanographic, and for other applications. MMT was our first customer back in 2015. With MMT, we did the first fast digital inspection survey in the North Sea. And since then, we've shipped to almost all contractors. So focusing a little bit on the fast and fast digital inspection, if we look at a conventional vessel, F is for fast. What we have proven across many pipeline and structural and other inspections at this point is that we can reduce the boat time by 70%. And this is achieved by essentially taking very large area, high resolution images. I'll show you what they look like in a few seconds, but also collecting laser data. So in the fast digital inspections performed to date, you can record images only and build 3D models from photogrammetry. But when we set out at the beginning, that wasn't the intention, and there's reasons, and there's good reasons why. I won't go into them in a whole lot of detail, other than to say feature matching and photogrammetry when you're traveling at 4 knots is kind of slow, and it gets in the way. So hopefully by the time I've explained what we mean by unmanned FDI, I'll give you a better sense of how we do things and why in that context. But fast digital inspection on its own typically reduces the boat time by 70%. Between 50% and 70% is typical. For pipelines, it's probably closer to 70%. That means there's less people on the boat, less people offshore for that amount of time, and obviously there's much less cost. So what that actually does, though, from a point of view of the data, is you've now got less time on the boat to process the data, and I'll address that as we go through this presentation. These are some of the vehicles on which our systems are integrated. So they range from autonomous vehicles on the left to Sabertooth type vehicles belong to ENI and Modus in the second column. Work-class ROVs, we have a lot of systems on work-class ROVs. Fast ROVs, as in the top, number 3 at the top, is the MMT, but also Deep Ocean and a few others. And then on the far right, we have towed vehicles, and these are typically used in fisheries for shrimp counting and sustainable fisheries, essentially to count shrimp and queen scallop nests in the seabeds. We've done quite a bit of work with the Fisheries Board in Ireland and Northern Ireland on those areas. But all in all, the whole idea is that we reduce the boat time, we reduce the diesel consumption and the cost. One small technical detail: when we record data, we timestamp it very precisely. So when we take an image, we do so in 1 millisecond. We timestamp it at the time of the acquisition, and we also then, if you do the maths on that, if we're operating at 3 images or 30 images per second, that means there's 30 milliseconds during which the lights are on. But for the other time, we turn on a laser and we acquire 3-dimensional laser data. And that time stamping and synchronization is critical to the unmanned operation, and I'll explain that as we go through the presentation. To show some of the images, this is the shark you can see in my background. It was taken in 2018 from a Modus Sabertooth AUV. The shark was actually fishing and taking some fish from the free spans as the AUV, and the guys in the boat said that basically there was a conveyor belt of sharks doing some fishing as the fish came out from under the free spans. If you look closely, you can kind of zoom in. These are UHD images. You can see very high resolution pictures, including down to the level of the shark's teeth. And remember, this guy is probably moving at about 10 knots to come in and get that. So the 1 millisecond motion freezes that movement. And that's one of the key things that gives us the high resolution, even when we move fast. Along with the images, we're acquiring laser data, and in the monochrome, the pure laser data, they're spatially and temporally co-registered. So we timestamp the images, we timestamp the laser, and then we can spatially correlate them in tools like IVA, and that's largely what is used today. So the laser operates at 1 frame rate, the images at another, and we can superimpose one on the other using the manual workflows. But our developments have moved away from that. So because we timestamp the color images and the laser data, what we can actually do is color the pixels of the laser data with the image data. So we have direct correspondence between every pixel in the laser 3D point cloud and the image data. And that opens up a whole wealth of possibilities in terms of what we can do with those data sets in terms of processing them. And where that comes in is for unmanned FDI, what fundamentally it does is it changes the workflow entirely. I've used the local guy, James Ives will thank me for it, I'm sure, X-Ocean's AUV, they're not very far from where we are here in Ireland. But essentially, in an unmanned world, we need to process locally, we need to process in real time, perform QC in real time, communicate to shore. And what that actually brings up is the whole idea that we should be eventing automatically. and doing the eventing while we're acquiring the data rather than at the other end. So if you look at the conventional workflows today, the data is collected, it's brought onshore, it's processed, the eventing is done, and the deliverables are generated. And we're saying, well, for unmanned operation, we need to rethink that completely. And I suppose the benefit of unmanned is if we have 70% less boat time in a normal operation and we have 70% less diesel consumption, then that goes to better than 99%. And of course, less time with an unmanned vessel is also got to be cheaper and less risky than normal visual inspection. So there are different risks, but those risks I hope are addressed by what we're developing in that context. So before I go into the workflow, this is a system that we are currently testing. It's planned for release in January. This is essentially very similar to our existing systems, but what we've done is we've put all of the subcomponents into one housing. So all of the cablings, the laser, the dual sensor, all go into a single housing, and they're all synchronized all in one box. And this is, to Al's point at the beginning of the conversation, we had to respond to the market. We had guys offshore in Australia ready to go out on St. Patrick's morning, and the insurers stopped the job because if somebody had an accident, they couldn't be sure that the hospitals would take them due to COVID. And what we realized that morning was, look, we need to accelerate this development and be able to send systems offshore without Cathix personnel with them. They need to be deployed, easily integrated and operated remotely without personnel on the boat. So for Cathix, we're putting this out early next year with the objective of using it on current operations for structural inspection, but also for pipeline inspection and many other applications. So there's a number of configurations to it. The specifications you can see, it's about 27 kilos in weight. To give an idea of the size of it, on a Sea Leopard ROV, it fits on the front of it for forward-looking inspections, and then we have a downward-facing version that sits comfortably underneath it. There's two cables that connect onto it. It's plug and play, and to be honest, probably in the first quarter we have a little bit of hand-holding, but I think after that we should be ready to deploy it without much more than that, with just remote support. On a work class ROV like the Shilling, we have what's the equivalent of our Pathfinder, where we have a port and starboard unit, and we can also mount a forward system. And these can all be daisy chained so that they're all triggered and synchronized. So essentially, multiple cameras, lasers, all timestamped and synchronized together so that we have an ROV. And typically, these work class ROVs can go up to 2 knots in 1,000 meters of water in the North Sea, and then on the faster vehicles, they can go up to 4 knots or on the UVs. But what's important, really, and what I want to kind of get across in this presentation is the data and the timing. So if we take the left, in a conventional survey, typically that's 30 to 60 days of boat time. And I'm using an example of about 500 kilometers of pipeline in this case. And in some cases it may be shorter, but if we take 60 days as the boat time for the 500 kilometer pipeline survey, when we go to fast digital inspection, typically that reduces considerably. So sorry, this is the 30 days. So we're typically talking about a 300 kilometer pipeline. So in the 30-day job that we have a few examples of this, we can typically reduce the time for that job to a quarter, which is about 7 days. But we haven't reported from a number of sources that the deliverables take considerably longer than that. And that's by and large because the methods for processing that data are the methods that were used before and adaptations of them. And we've done quite a bit of work to make sure we comply as much as we can with those workflows. But as we go to unmanned FDI, what we're aiming for is essentially, in the short term at least, for every day of data acquisition, that it's no more than a day of processing. And it can be much less than that, but we're at a place where we're trying to reduce that. In principle, if we go to the far right here, if we and when we develop and deliver these systems in the field next year, we expect that we will be able to do the eventing in real time. But there is complications. In other words, we're still waiting for the right unmanned vessel, we're waiting for the ROV, and all of those parts have to be right also. So this isn't just a case of Cathix development. We need to work with the providers of those services in order to get this whole system working. But in principle, standing on its own today, if we were doing this for a current vessel operation and developing for that alone, it is quite feasible that we can perform automated eventing and deliverable generation during the acquisition time on the ROV. or even on the AV for that matter. So to try and explain that in a bit more detail, there's 4 elements to it. The first element is real-time processing. So we want to process data real-time as it is acquired. The second element of it is inline processing. And the difference between inline processing and real-time, when I talk about real-time, I mean, keep in mind that FDI is 4 times faster than conventional survey. So we're already working in a compressed time frame. So for an hour of conventional survey, you've got 15 minutes, which means that the data rate is 4 times faster. So real-time processing, the applications of this are pilot assistance, pipeline tracking. We compress the images so that we can transmit them to shore, and then we do heartbeat monitoring. Essentially, we monitor the progress of the survey. For the inline element of that, the automated eventing part, it's inline because it's not on the frame rate of 1/60, right? So our laser can operate, let's say, at 30 lines per second or 60 lines per second. Real-time refers to 1/30th of a second. When I talk about inline, I'm talking about we might take multiple lines of laser, look at the stats on those, and then accumulate that data to say, so it's probably within a second of acquisition. So the inline eventing is one of the major developments we've been undertaking. And with that, then we can tag those events. What that then lets us do is, once we've got our real-time processing for situational awareness, our inline processing, we can then look at the priority processing of that data and generate deliverables while the USB is offshore. So on a 9-inch rack on the vessel, the whole idea and the way our deliverables are structured, as I said at the beginning, we're not doing feature matching. So how we actually generate the color point cloud is by aligning the pixels in temporal and geographical space, coloring them, and then using the images and that color point cloud to effectively generate meshes and orthomosaics. It doesn't require photogrammetry. In the past, we have found some issues with repeatability, reliability, and particularly the time it takes to process photogrammetry data, the processing overhead. By avoiding using that, we can actually generate these deliverables very, very quickly. And that leaves us with the very last piece, which is the deliverables and reporting. So as soon as the USB arrives to port, the objective is that all of that data gets uploaded in an Azure box to the cloud in a way that now you can start to do inspection. And at the very end of the presentation, I'll give you a bit of a snapshot of what that looks like for structural inspection. So if we just very briefly, I won't go into a whole lot of technical detail, but to explain the word machine vision, which I used in the slide title, in the presentation title, for unmanned fast digital inspection, machine vision, if we look at a single laser line in cross section, in camera space, not even in real world space, what it gives us is essentially a geographic map, or sorry, a mathematical map, dimensionally accurate of the pipeline or the structure that's flying over. So in other words, it's a height profile, and it's accurate to the millimeter level. So what we've actually got in this case is from our Pathfinder system, where we can extract from this single line of laser data the lowest point on the seabed. We can extract the top of the pipe, the edges of the pipe, and the seabed. And what that actually lets us do is extract information around about the pipe and the seam. We can extract it for single laser lines or multiple laser lines. And I'll talk a little bit more about that, but in effect, what differentiates machine vision from machine learning is we're using a physical measurement acquired in real time to draw a conclusion on what is in the scene. We're not using algorithms and feature matching and blob detection. We're actually taking live laser data, extracting the information in the time period of the next laser line, accumulating that data and using it to extract information on the scene. And that opens a huge number of possibilities in some of the things you can do. And I won't go into them all now, but over the next few months, we'll relay more information on that. The other things that are important are, so if you take that, you can say, well, look, I want to track the top of the pipe. We can also do image compression. We do image compression in our imaging systems already. But what that actually means is that if we take a HD image and decimate it, we can relay images and the top of the pipe data in real time to a pilot onshore and consume less than 20 kilobytes per second of bandwidth in doing that. And that lets us do things like real-time QC, real-time piloting, and it's fundamentally taking less bandwidth and is more reliable than using video, for example. So the next iteration of that, if you think about the automation, is to actually close the loop. And we have with a customer in Italy, shipped what we call a pipe tracker, which is a real-time feed into the underwater vehicle so that it can maintain its trajectory on the pipeline. So where that also matters is in the longer term, if there's a loss of communication between the underwater vehicle and the pipe and shore, there is the capacity to build automation into the vehicle with this data set. This is what it looks like. This was an early development. It was done about 2 years ago, but it gives a picture of it. So on the right-hand side, we have the pipe, the laser data in camera coordinates. On the left, we have the corresponding image as we fly it. The data on the left is essentially giving a feed that we're locked onto the pipe. So the crosshair in the center of the screen is the ROV position. So what we're able to see is as the ROV travels the pipeline, we're able to, in camera coordinates, in real time, see and visualize both the images and the features. And where this gets kind of interesting is if you look at the finer detail of what's happening in these lines, you can see the little dots and the blobs. You can see the red on the left. So where there is a feature or a physical structure in the scene, the laser picks it up and we can detect that also. But in this case, we're trying to track the top of the pipe. So we're extracting the apex of the pipe data, the sides of the pipe. You can kind of see where it stops there, where there's a tear in the field joint wrapper, that there is a rise. So this gives us real-time dimensional data. And that's one of the aspects. This happens in the FPGA, in the sensor. So we can feed that out as we collect it. If we take that a step further, we can do similar with free spans. So we have no requirement for nav processing, remember. We're literally looking at the structure of the measurement data as it feeds from the camera. So this lets us do segmentation of the pipeline and the seabed. It allows us to take endpoint measurements across the pipe. And remember, we've also got the corresponding images. So anywhere we have a detection of a signal on the free span, we can acquire those images and separate them. So think about this in an unmanned environment where as soon as we detect these changes, we can actually start to sort and separate that data by tagging it and put that in for priority processing in the next stage. Likewise for rocks and objects, dropped objects, field joints, anodes, there's a corresponding signature in the laser data that facilitates that. Just conscious of time, I'm going to skip through some of this. So essentially, priority processing refers to if we've gone out and we've collected these events, we then have the capacity to generate deliverables on those events, either in color point cloud, in mesh, orthomosaics. We've been doing this for a couple of years with existing data sets, and it comes down to really what are the requirements of the integrity engineers. And by and large, it seems that the color point clouds are particularly useful, particularly for free spans, but also the images then give verification and validation of what's seen in that data set. This is a much more fancy picture of one I've showed earlier, so I've covered most of the points in it. Where we're trying to get to is automation, and the whole idea that from the point of view of using laser data to perform real-time eventing, where we want to go is fully autonomous, unmanned, fast digital inspection. So all of the elements that I've talked about are there in a way that with a relatively low risk development over the next 12 months, our ambition is to be able to event, and it may not quite look like this, but to be able to pull these events from the data set as it is collected, to provide cloud access to that data through an inspection machine. And that inspection machine is really, it looks like this. So essentially it's what we call CX Observer. And in this case, I'm going to talk about structures because if you look at work we've done with our clients in West Africa or in Australia, the whole idea of it is much like pipeline, we do the work in 1/5 of the time, right? So we can reduce the time it takes for an inline T or a manifold by considerably, typically up to 80%. We do that by essentially flying the structure from a distance of 2 to 3 meters, doing QC on the data as it's acquired, but particularly doing the inspection onshore, not offshore. So what we've built is what we call CX Observer. It's the manual inspection tool that allows the inspection engineers to review that data, tag that data, to mark particular events and features on the structure in 3D, to review the images in 2D, and then to store those data sets, and particularly to integrate them into Cobus and into Nexus. So by the end of this year in December, we're doing it at the moment, we'll have a full Cobus integration. And the whole idea is that this process, much like the pipeline, if you start off and think about the manual inspection workflow, which we have worked on so far, the next obvious iteration is in 2 years' time when our clients go out to do this inspection the next time, we actually have the data in the right format, in a way that people can interact with it instantaneously, and start to build automation into it in that way. So there's two elements. There's the current way we do it. There's the longer term objective, which is to automate it through machine learning, machine vision. And for structures and pipelines and whatever it is we're looking at underwater, the whole idea is we have real-time data, we have QC, pilot awareness, and the same principles apply. But the whole idea is at the end of it, we have this data in a format that is standardized in the cloud so that inspection engineers and integrity engineers can start to use it for integrity management, which is really what we're all about. But from the unmanned fast digital inspection point of view, this approach essentially gives us data that improves and facilitates unmanned operations, both for pipeline and for structures. And then year on year, this methodology allows us to do things like pull up the previous point cloud, the previous image, it gives us that interface to both manage the data and pull out the particular anomalies and track changes, and essentially forms the basis for our data analytics platform, which is effectively automatically pulling up specific defects on specific structures, but also comparing them across all structures. This presentation isn't about machine learning, it's about unmanned FDI, so I'm not going to talk too much about that. So to conclude, hopefully not too late, our fast digital inspection data method was developed for automation. It wasn't developed for the manual workflows today. So our objective is to reduce that time, the time of processing and deliverables, or as our clients call it, the data product, to the same time as acquisition, but in parallel to reduce the time of acquisition, even in unmanned operations, to 1 quarter. And to do that effectively, the workflow changes, the deliverables change, but we're working with our clients to define, okay, what are the deliverables required for, what's important to integrity management, and then what's important in terms of reducing costs. So from a Cathix point of view, we're doing this already for existing operations. We're accelerating it due to COVID, and over the next 4 months, 5 months in particular, we expect to be performing unmanned operations using this capability. Thank you.
Thank you, Adrian. We're going to have a half-hour roundtable at the end, so I have some questions. I'm sure the other presenters will too. So appreciate your presentation.
Thank you.
Okay, so we're going to move on to the second talk, which is by Hannah Thomas. So I'll give you a second, Hannah, to get your take over the screen sharing. So Hannah is the lead data science person at L3Harris ASV. So many of us in the industry know the work of ASV through their vessels, but I know they've been doing a lot of work on the sort of software and data side. So she is an expert in data science, big data and associated technologies and machine learning. She's worked across a number of industries, including investment banking and autonomy. Hannah has a master's degree in mathematics and computer science from the University of Oxford. And she enjoys explaining and teaching machine learning and data science techniques to industry. So take it away, Hannah, thank you. You might need to take yourself off mute, actually.
That would be a good start, hey?
Awesome. That's all right, we're all getting used to this.
Here we are. All right. So hopefully you can see my screen.
Yeah, it's come through.
Excellent. So I'm very happy to be here today talking to you about the machine vision techniques that we have developed at L3Harris ASV to enable our safe autonomous navigation. So I'm going to start with an overview of our autonomy system, just to put things into perspective and explain what we use machine vision for and why it's so important for our autonomous navigation. So we start with the perception of the system, where we take in raw data from our various sensors, cameras, radar, LiDAR, AIS, various charts and external data feeds. And then that gets fed into the intelligence system. And the first thing the intelligence system has to do is make sense of this data to build up a big picture situational awareness of the environment around us. So it'll take in all this data from different sensors, which have got different types of information and different amounts of noise and things that need censoring through. And it will make sense of that, turn it into a situational awareness picture, and then it needs to turn that into some kind of decision. So we need to take this information, evaluate our options, and decide how we're going to react to that. And then having made the decision, we then need to carry it out. So we'll send instructions to the controls that say turn left to avoid this collision, or whatever the action is. Now, as the AI of the system develops, we're finding that the human-machine relationship is changing. So we have this human-machine feedback interface. But as I say, as the intelligence increases in the machine, we're finding that the form of that relationship is evolving, and it will constantly evolve as we develop. So where the machine vision comes in is a crucial component of the situational awareness of the system. So one of the things we do with machine vision is object detection and classification. So we will train algorithms that can look at data frames and scan through them and identify where there are objects of interest for us. So here's an example of that working in action. So what we've got here is our autonomous vessel transiting out through the Solent. And on the right-hand side, you can see there are some sailing boats parked up. And our autonomy algorithm is detecting that we've got those sailing boats there and alerting us to the fact that they're there, and we want to avoid them to avoid a collision. Now, we're constantly going out in different environmental conditions to test our algorithms in different scenarios. And in this particular case, we went out on a day where it was all a bit horrible and overcast to test that the algorithm could still work in these grey and kind of muggy conditions. Now, in principle, that might sound like a fairly simple task to do, but it's actually, to get a computer to do it, it's actually really difficult. And the reason is because it's really difficult for us as humans to really define what the problem is that we're actually trying to solve. So for example, when we're looking at objects visually, the same object might have a variety of different visual representations. So for example, if I'm looking at a chair, I could describe a beanbag as a chair, but I could also describe an office chair as a chair, or a dining room chair as a chair. So all of these things look very, very different visually, and describing what that looks like, just describing how to identify that just from visual representation alone is a really difficult problem. Equally, there can be things that belong to very different classes that actually have a lot of visual features in common. So for example, a basketball and an orange, both round and orange objects, but actually how you would define them, the classes that they actually fit into, are completely different. So sometimes you get a bit of kind of blurring and obfuscation between the class boundaries that can make it hard for the machine vision algorithm to work out how to differentiate, how to separate the different classes. And also, images on their own don't have any depth perception. So there's all this contextual information that we have as humans that help us to make decisions about what we're looking at that a machine just doesn't have. So when we're trying to train an algorithm, or when we're trying to develop an algorithm to identify what different objects are just purely looking at their visual features, it's a difficult problem for us to describe how to solve that as humans, and therefore it's a difficult thing to get a computer to do. So this is where machine learning comes into play. Because, as I said, it's a hard problem for us to define, we can flip the problem on its head and get machine learning to learn directly from the data. So rather than us having to define a mathematical function, we can get the machine to work it out for itself. But to do this, you need to have enough data to comprehensively teach your algorithm the problem that you're trying to solve. So for example, in the chair example, if you want it to learn, what the different types of chairs can look like, then you have to have the variety of data to cover all the different scenarios of what a chair can look like. And And also another problem we have is that because the function is learnt by an algorithm, it's not something that we've worked out for ourselves. And because it's a vastly complex algorithm, and the kind of features that it will pick out from the image and group them all together, and the way it might group them all together could be really complicated. And it could even think up things that we would never have thought of ourselves. So that can make it really hard for us to really know what it's actually learnt beneath the bonnet, and to really understand that the resulting algorithm has got that discerning capability to really be able to tell you what a chair actually is, and define, and to be able to define things with certainty. So let's talk about the process for developing a machine learning model to illuminate this process a bit more. So I mentioned how data is really important. Now, a lot of people are probably aware that typically for machine learning problems, you need lots of data, but really the key is having the variety of the data to really teach the algorithm what you want it to learn, and make sure it doesn't overfit to a particular scenario if you don't give it enough data. So we are always going out collecting data in the real world whenever we get the opportunity to cover the variety of different environmental conditions and different parts of the world where things look different, the sea looks a different color, and all sorts of different things, different factors that might potentially be confusing for an algorithm. But also to give us an extra bit of control over what we're feeding into our algorithms, we make use of simulators. And once we've got all this data, to make it useful for the algorithms, of course, we have to tag them as well. Now, with simulated data, we can automate this process because we're controlling what's being generated. With real-world data, we have to go through and do the labeling ourselves. So we've developed some data labeling tools that will help us do the job. And we have a semi-automated labeling process where we'll have an automated process that runs through and does a first pass, and then we can go through and refine manually. Once you've got your data ready to be fed into an algorithm, and maybe you've done some sampling, made sure you've got a good variety, a good spread of examples to give your algorithm the best chance possible of learning what you need it to learn. We then feed it into our algorithms, and they'll do a bunch of training. And because it's quite a complex problem that they're trying to solve, and quite a complex function that it's trying to learn, this can take a long time to do the training. And then as a result of that, you get your visual object detection out, which we can then run on our boats and feed into our collision avoidance algorithms. So data collection, I mentioned how this was a really important thing, and capturing the variety is really important. So we've been collecting data since 2006. And as I said, we're going out in different conditions all the time. Whenever we get an opportunity, particularly if it's a new location that we haven't visited before, we're always going out and collecting as much data as we possibly can. And we'll use different cameras, we'll use different sensors, we'll try and get pictures of objects from different angles. And as I say, we'll go out in different weather conditions and do all sorts of things to get as much variety as we possibly can in our data set. And we're also interested in anything that makes the visual scene look different. So if we can capture pictures with sort of water on the lens, or anything, go out at nighttime as well and capture infrared images, anything that makes it look different. That's all interesting to us because it's the variety that we need. Okay, so once we've generated our data sets, we've done some training, we then want to understand how good are our models actually at identifying our different classes of interest. So here I've got 3 different models that I'm comparing, and there are plenty of classical approaches for doing this. In this particular example, I'm using what are called ROC curves. I don't know how much people know about ROC curves, but essentially the more the orange curve is pulled up to the top left-hand corner of the graph, the better the classifier is at differentiating between the different classes. And this is really good at giving you a quick overview of roughly kind of how the classifiers are performing. But what we're really interested in is how well has it actually learnt the problem? So how well is it actually understanding what the different classes are and how to define the different classes visually? So I mentioned how that was quite a difficult thing to do because the machine learning algorithm has worked out some features that it thinks are useful for solving the problem beneath the bonnet, but we don't necessarily know what they are. So what we need is a technique that can give us a bit of insight into that. So this is an approach that we've developed to achieve that. And what I've done here is I've taken the original images and I've represented them in terms of the features that are learnt under the bonnet of the different algorithms. And typically when it's represented in those kind of features, each image will be in a really high dimensional data space. So it's something that's difficult for us to visualize. But we've got a technique here that enables us to project the data down into 2 dimensions so we can visualize it. And then I've overlaid it with the information about which class each image belongs to give us a feel for how well we're really separating out the different classes and how well the algorithm is really starting to understand how to differentiate the different classes from each other. And by the way, this map actually wraps around top to bottom and left to right. So what you actually get is a donut, but for the purposes of making it easy to visualize here, I've flattened it out. And what we're seeing is in models 1 and 2, there's quite a lot of confusion. So basically, the more speckled and the more overlap there is between the different classes, the more confused the algorithm is about how to differentiate different classes out. And the more well-defined the different clusters are, the better a job it's doing. So certainly model 1 looks very confused. Model 2 is starting to do a bit of a better job. So these features, this is an indication that these features are probably better for solving our problem, but still it's not really brilliant. However, if we look at model 3, what we can see is that it really is actually learning much better how to differentiate the different classes. And what we can do is we can look at the specific examples of things that it has classified really well, or things that it does appear to believe that are in the center of the cluster, and other things that are sort of on the border that it's getting a bit confused about. And then we can analyze those specific examples and start to understand what kind of features are driving the algorithm's performance and driving its decision making. Okay, so that's our object detection and classification capability. There are other things we use machine vision for to aid our navigation system. And one thing is target following. And this is the beginnings of an autonomous docking system that we are developing. So how it works is we stick, in this example, we stuck a QR code to the back of the support vessel in front, and our autonomous vessel behind is using the positioning of the QR code in front to align itself to follow in the wake of the vessel in front. So this is an example of us using machine vision to position ourselves very precisely in relation to another object.
Hannah, you've got about 5 minutes if that helps.
That's great. I'm on my final slide now, actually.
Oh, wow.
That's great. So we've got our 360-degree bird's eye view, which is really useful for remote operators when they're navigating in a tight scenario, if perhaps they're trying to dock or they're navigating in a heavily cluttered environment. And we've got our 360-degree camera array, and we can project the images down to give that bird's eye view of what's happening immediately around the vessel and aid the operator, give them a very clear picture of the obstacles immediately around them and help them to navigate. So that is a quick summary of the various types of machine vision work we have going on at ASB. And how we use it for our autonomous missions.
Brilliant. Thank you very much, Hannah. I have a few questions. I'm sure the other panel members will too. So I wanted to introduce our third talk, and Felix from Norway is going to talk about Pale Blue, which is an industrial VR company. Felix is the managing director and the leading technical expert. And he's worked lots of different places in technology and software, including ones that we all know like Aker Solutions and Sun Microsystems, but also other small and medium-sized enterprises. He's covered a range of roles, including software engineer, system architect, project manager, and now managing director. Pale Blue leads the way on developing virtual reality, augmented reality, and 3D simulators for real-world solutions, helping clients to digitize their data, make better training, streamline workflow, and improve safety. Felix, looking forward to your talk. Take it away.
Thank you, Alison. I hope you can see my screen.
Yes, come through.
So the topic that I'm going to present today is called Simulators and Artificial Intelligence Working Together. My name is Filip Gorbacevic, and I'm the one of the team members here at Pale Blue. What Pale Blue as a company is focused at is different kinds of simulator and training systems. Typically, those are used for humans, but it's not unthinkable that the same systems are in some contexts also used for machines and artificial intelligence. All through the years, we've been focusing on different segments, even though our main focus area is within the industry and the energy sector, where we produce different kinds of training simulators, including the fancy technologies of virtual reality and augmented reality. So the different types of systems really span from screen-based to virtual reality-based to operational chairs with joysticks. And those systems allow to reproduce specific operational conditions for not just human, but also human-machine interaction and team training. There are some known pitfalls within the area that we've been operational, and that is the incidents and accidents when there's a lack of awareness, insufficient training, not being exposed to the full work scope, not being aware of the other team members. And all that can lead to production stops, operation stops, damaged equipment, and missed deadlines. That's some of the potential outcomes here. So traditionally, there's a number of tools that we have been applying for the industry in order to help addressing those problems and avoiding those problems. Virtual reality and augmented reality are just two of these tools. And of course, there's a number of different control options that one can use when controlling a certain machine for operation, whether that's with hand recognition, virtual reality gloves, controllers, or the traditional operator chairs. I mean, there's a lot of flexibility in how one can control an operation, whether that's spanning from manual training, whether that's going to the full actual operational control of the machine. So all these different options exist, fully dependent on the project budget, fully dependent on the amount of flexibility and the interactivity that is needed in a certain operation. It's also important that when we're training the humans or when we're training the machines that we are trying to achieve one-to-one behavior in the simulated medium. We want to reproduce the processes as they occur so that the resulting training systems can also be quality controlled and verified, such as, for example, giving an example of International Marine Contractors Association approving some of our digital systems for training of personnel due to the nature that the conditions, the pressures, the gas mixes, the working conditions are reproduced very close to reality in a digital setting, in a digital simulator. We want to immerse the humans, we want to immerse the machines. With that, we want to give users freedom of movement in different synthetic environments, whether those are on land, whether those are underwater, subsea. We've done a number of systems for commercial diving. I'm sure there's a clip coming on that as well. So in this, again, we need to balance what kind of tool set we're able to use. And typically, we aim to look at the off-the-shelf available systems, such as this. This is a standard issue of VR headset, typically available in the Best Buy or similar electronics store, where we would have to construct additional elements of the picture not really available in the sensors. If you see that the only sensors available are the headset and the hand controllers, meaning that the system doesn't really see or detect anything that's happening below the waist. And those are the parts that we have to reconstruct by prediction algorithm using inverse kinematics, trying to position the legs as they can be in this specific moment of time. And this adds to the immersiveness of humans, but also this adds to the immersiveness of machines, because machines would then scan the surrounding area. If it's the ROVs and humans working together, we want to produce an artificial point cloud, and also for the virtual humans. So this is one of the examples where we want the visuals to be more or less corresponding with the reality. So whether the visual sensors or the LiDAR sensors would be able to detect a realistically looking environment. Now, here's another example that comes to making synthetic environments for underwater operators. In this case, this is a system for training virtual reality divers, where this is commercial divers operating. Then again, they have to go through the diving bell setup and lockout. They have to open the hatch. They have to go out to the seabed, where they interact with others, where they interact with the ROV pilots. So this is again a simulated environment made to be rather realistic, made to simulate the environment and with the ability of changing and varying the amount of visibility, say, on how many meters visibility one would be able to get in a certain scene. So this is where the human operators again can be immersed in that medium, where they can rehearse in different scenarios, and you see the ROVs are partaking in that as well. But this is one of the I think interesting examples where it's possible to run through an operation. And we all know that the machines have the simulation capabilities. All the PLC, the programmable logic controllers, have a simulation mode that allows us to go and test them out in different scenarios and conditions and see how the autonomous logic will work. But the truth is, most of the operations, they also involve humans in the same scene. So this is why our focus has been on combining machines and humans in the same virtual scenes for all those different operations, and making sure that we can really operate the equipment by machines and by the humans. Well, yes, with the checklists and procedures, and this is where you would go through the normal operations as well as the emergency operations. Operating the machines, and in this case the ROVs, we are looking into the modern ways of how the interactivity can be done for manual control and for autonomous controls. This is when we're mapping, again, standard issue VR headset with the VR controllers, and we're mapping that to the ROV's manipulators, in this case a 7 function and a 5 function. So we're solving essentially an inverse kinematic problem of positioning the manipulators the way that the human hands are positioned, and following up with all the joints that are found in an ROV arm. So this is yet another way of how this technology can be plugged in for certain prototyping, for certain, not just training, but also operations. And in the studies that we've done, we see that this can be pretty understandable and straightforward, even though you have to learn the original manipulators quite a bit before you can operate them. The master controller arm of the 7 function, the joystick for the 5 function. Going into this method of operation, it becomes much shorter time for learning how to do certain stabbing and certain underwater manipulator related operations. So programmable logic controllers that are driving the autonomous machines on the subsea, on the top side, the way they are set up is well known that they have the real motors that they are able to run back and forth, and they have the real sensors. This is their impression of the outside world. They can sense the environment, and they can then affect the environment, either by moving through it or really interacting with it. So in our simulated or synthetic environment, we take away the real components and we plug the very same programmable logic controllers into the virtual counterpart. And then again, many in this industry are doing a similar thing when we're taking away the real feed from the cameras, the real feed from the other sensors, and we're replacing that with the virtual feed from the virtual replica of this world, where machines then, well, are essentially fooled by thinking that they're sensing certain work conditions, and they are able to then run their virtual motors, not being aware that the whole machine experience is not real, but synthetic. So combining this virtual sensor and virtual motor and a PLC, we produce a digital twin for real equipment, because there's a PLC running the brain, but we have to create virtual, if I may, physical copy of the machine, in having the geometry, having the thrusters, having the manipulator arms, and then we put that virtual copy, the digital twin, into the virtual environment. So this is where the PLC, the brain, is disconnected from the from any reality, and it drives the digital copy in a digital world, interacting with the other digital actors. Now, for the autonomy, we know, well, based on the NASA's level of autonomy of automation system, one can list 8 levels of autonomy. If we start at level 1, this is where the human alone can execute the decision. Now on the level 2, the human is the prime source of execution. And then as we move upwards, the amount of autonomy grows to when the system still allows the human to have a certain veto time before the execution, context-dependent, pre-programmed, or on the level 6, the system allows for the override after execution has taken place. Level 7 and 8 are higher, with level 8 when there's no any allowance for the human interaction and the system performs fully autonomously. And then again, in different segments, there's different level of adoption of how autonomous the operation are. If you take the autopilot on the jets and the airplanes, they obviously have taken it rather far. And if you're thinking, say, today's drilling systems, they're still quite low. They're not really on the upper part of the spectrum. So our task then in here is to enable the AI to use the simulators. We have to make a copy of the environment, because that's where the machine is going to be immersed in. We have to copy the environment in the ways that can be read by a machine. We have to copy perhaps the visuals. Sometimes we have to copy the thermal signatures of the environment. And if there's a laser scan, we have to make sure that our virtual world allows for a virtual laser scan that can be then perceived by a machine. Here we come to an interesting way of operation. Then again, we've been looking at a lot with the drilling operators, which comes to these 4 steps when we have the real environment, but we have the virtual environment as well. And we've trained our machines so they know how to operate. But still, when we're operating in an unknown environment such as drilling, we never know how the drilling process will actually go, just because there's a lot of unknowns and a lot of unknown variables in the lithology, in how the drill string will go. So we have come with the set of steps that allows the machine to coexist in the real world and in the virtual world. So perhaps this is best illustrated by this, that AI can operate in 2 worlds at the same time. First, it has the digital twin of the environment, of the machinery, of the situation. And then each specific frame, it can try a certain move in its prediction model. So let's say it can try the certain strategy for drilling with the higher RPM, or it can try to do a certain rotation in the drilling. And then based on the digital model, it can see, all right, I've tried these different ways, and according to the digital environment, the best strategy is this. And that's the one it is applying to the reality at the same time. So it's 2 processes happening in parallel. When the digital and real coexist, when the 2 processes coexist, but the machine has the opportunity, like in chess, to play out different moves going forward, pick the best one for this specific moment in time, apply it, and continue with the real process. And again, the real feedback from the real drilling or the real operation will feed back to the digital twin, updating the digital twin. If you have a different experience in the lithology, if you have a certain shift, that feeds back to the digital twin, allowing you to keep your model up to date, still make predictions, still try different strategy, but align the virtuality as the reality is. Lessons learned. Distributed collaboration really helps now in the COVID times. I think it's becoming rather understood by many, where we can connect people and machines from different sites. People don't have to be in the same room anymore. We do a lot of distributed training. We do a lot of operational checkups that are distributed and not bound to the same room anymore, just because we have these digital twins that allow us to do these digital operations. Just give an example, again, maybe outside of the industrial area, as we've been lucky enough to get started to work with the space industry. So for this year, we've done already a number of modules on the International Space Station, and our training has been more or less a copy of what you see here on the screen. Our astronauts being trained, and some of the autonomous logic meets online, connecting from different countries. So if this is a project prepping, if this is a certain study for the equipment, it's completely possible to take that online. There's a number of benefits using simulators. Again, I would say that training simulators for humans, that's a known thing. Training simulators for the machines, maybe not so known as of today. And then again, operational simulators that allow the machine to perform better and make better decisions with having digital and physical model at the same time is something that we're just getting into. It doesn't look like this will take away the need of real hands-on training, real hands-on operation on site, but this can be complementary to what is being done already, and simulators can make certain things easier and more effective. So combining those things, just a small demonstration really of how one offshore operation of taking a module from the oil rig and then onto the seabed can be done in a constellation of a number of humans and machines working together, and then we're getting 10, 15, or maybe 20 participants at the same time working in this visual replica in this virtual world so that they can all cooperate and conduct a certain operation in all the different roles that they're having. So it's not single role training, it's all the different roles seeing each other and being able to interact to solve a certain task. With that, we'll conclude. Thank you.
Thank you, Felix. Pretty much bang on time as well. So now we go into like kind of a round table. I wonder if we start with you, Felix, as you finished. So many of the ideas you're sharing seem completely relevant given the really difficult time we've all been through and trying to get work done. I wonder if you could say something about the kind of uptake you've had with, trying to get people ready to go offshore when, it's difficult to bring people together. I mean, it seems like your distributed collaboration model really fits with the kind of constraints we've got at the moment. Oh, I think you might be on mute, Felix, sorry. I see you lead on. Now you're back.
Right. So what we've been seeing, well, then again, this year, it's more visible than what we've seen in 2019. People really now tend to start realizing the value of being able to train and meet in 3D. And we've done, I think, a number of trainings and sessions this year when, for the digital copy oil rigs, we've done joint sessions where I think you can come with a number of good arguments there. If there's an upcoming shutdown, that is often so, you would be able to execute it more effectively if you run through it. If there's new people ramping up, then you're able to ramp them up also in the virtual model.
And I guess as well as you can get started while people are still in their home location, right, before they have to travel. That surely must be so helpful for operators and contractors who are trying to get work done.
Absolutely. I mean, there's quite a bit saving on travel just because the hardware is off the shelf. So as long as you can get a VR headset in the nearest Best Buy or similar store, you should be able to go. And then again, not all of the experience has to be in VR. Some could be just in 3D using your screen. So then you wouldn't even have to get a VR headset.
And I can see in some of the work I've been involved in, people are starting to use these augmented reality to kind of do what if, discussions and get people to have better situational awareness. Are you saying the same stuff? So I'm thinking beyond just training, but actually supporting operations. I imagine you're seeing the same thing come through now.
Probably the biggest trend that we're seeing now is the remote support when there's the back-end office with the engineers, and then you're able not to travel each time when there's certain assistance needed offshore. But instead, with HoloLens or similar setup, you're able to bring the engineer remotely and enable the technician in the field to operate machinery that perhaps he is not fully aware of the full specification of, and remote support through augmented reality allows that.
Okay, and then I just one kind of other follow-up question. I open up to the others. I know because all companies must be engaged in this, trying to sustain the quality of the digital twin. Fidelity of data is always challenging. How have you helped your clients, overcome some of those types of challenges? Because I know that must be a real challenge for everyone, right?
That's a pain point for many. Then with installations out there, not everyone has an updated CAD model, unfortunately. Sometimes you have to remodel it based on the laser scans, or sometimes we just go by the photos. Sometimes they just send a bunch of photos of the installation, and we have to blend that with the previously dated CAD model. So, I mean, it's a struggle for many, and not everything is perfectly logged back into the CAD when there's a certain modification being done in the field. But there's a number of ways how to address that. When there's no CAD, it's possible to use other data, including photo, including photogrammetry, when you're just using the video feeds from the ROVs or so to reconstruct the field as it is today.
Okay. Adrian or Hannah, did you have any kind of comments or questions? I imagine, Adrian, you must, because you must be helping other clients do somewhat similar things with some of your hardware and software offerings. I can see you're on mute still, so I thought I'd give you that tip first.
Very good. I never learned. It's I think it's interesting. I won't even claim to be. I know very little about digital twins. I suppose what kind of resonates with me from a Cathix perspective is what I think we're providing into that environment. And I suppose the other thing I'm not sure on is the timescale for the type of work that Cathix does. If you look at the different applications, but where I think it gets fascinating is training is one thing, but education, and one of the long-term objectives for what Cathix is doing is, apart from, let's say, the oil and gas, we have, if you look at the work we've done with the Alfred Wegener Institute, or the work that they've done with our systems, let's say, they're able to track Arctic ice melts by looking at dropped rocks on the seafloor. And it's one thing what we're actually creating is real data for that virtual environment. And I think from an education and awareness point of view, it's fascinating, because if we can kind of make the data accessible on that scale and create that environment for interacting with it, particularly, like I'm an old guy, but for somebody who at 5 years old can use a smartphone and you know is going to be using VR headsets in a few years' time, I think it's fascinating, and I think it's we're certainly looking at it beyond, you know, even the next 5 to 10 years. But how do you interact with data? And we're trying to comply with, you know, workflows from 10 years ago or 20 years ago today in one hand, but at the same time look at that going forward. So I'm more informed than I was 2 hours ago for sure, but I think I have a bit more homework to do.
So Adrian, sorry, Felix, I was going to say, sorry to interrupt, maybe both you could address this point, because I think there's something about the digitization and the digitalization where you like reimagine the workflow. And all three of the talks I saw that coming through, where we're starting by just digitizing and then now we reimagine how to do the work.
Right.
So, sorry, Felix, you carry on, but I thought that was worth mentioning because it comes out in all three talks.
I was just to add that, yeah, education is something that is really picking up as well with these technologies. It also goes to when there's say when you have to study the environment and educate the others on how the environment is evolving. That's one point. That you can also educate on the equipment. And when you're educating on the equipment also, you'll have to look into, can this be certifiable? Is your VR or 3D experience just a nice visual part to it, or can it be approved? Can it get a license after using it? And then it goes back to the certifying organizations such as DNVGL, such as IMCA. And we can see that they can kind of get very hands-on with this, and they are now working on the not just the simulator regulations, but also VR. Can you have a Class A fully immersive simulator training in VR for either crane or ROV? And the answer to that is yes, hopefully very soon.
Okay, that's good to hear. Adrian, sort of following on, I was really interested to see how you started to address kind of some of this AI at the edge type kind of problems, because I know, you know, you must know this too, is when we're moving to these better sensors, we're creating much more data, and less vessel time means processing comes onshore, and obviously, you know, it is expensive to process giant data sets. This is a new workflow, right? This is digitalization, but it seems very promising, right?
Yeah, I think so. So how we're tackling it at the moment, actually, because we have, if you take a very simple case of an ROV flying around a subsea structure, collecting anywhere between 10 and 25,000 images, as well as, you know, lower density data, 3D point cloud data. You don't need all of that to do what needs to get done. I'm becoming much more familiar with the costs of cloud-based storage, for example. So in terms of the volume of data, there's no need to put it all in. So I think how we're tackling it is you know, and keep in mind there's many applications, and in some cases our clients just don't want us to see the data. We're never going to see it. So the most important thing is getting information from data. And that's kind of what the presentation was about. It was about, well, on the vehicle, you need to know where you are and what you're looking at, and you need to know, well, these are I think the term is the data product. I need to know where my mines are or where my free spans are. and what they actually, what is the data? Are they 20 meters long and 3 meters deep, or are they 2 centimeters deep, and so on? So all the data in the world is meaningless if you have to trawl through it, and and that takes time, and that's a little bit of the historical. So I think what we're trying to do is, and the product actually in development is called Cathix Insights, where we're extracting information from the data at the time of acquisition with the view to dramatically reducing the amount of data that you have to store. And let's call it, what we're doing is we're generating, using manual interactions, and almost a little bit like what Felix is talking about, using that training of the data sets to teach the machine vision and machine learning systems what to look for. And then for our clients, if they have all of that data, you can very easily see a route to automation, but it has to keep in mind the business, because if you reduce the cost of the operation by 70% and you reduce the number of people by 70%, it doesn't mean the work is free, right? So but somebody somewhere is going to try and make money, and it's either going to be in the storage. So you have to look at the whole system. And for Cathix, in a rapidly changing world, we're trying to do the right thing for our business, short term and long term. And I think that's a bit of a balancing act. But for sure, I think if you focus on just collecting the data as efficiently as possible, extracting the most valuable information from it, and doing it with the least cost possible at all times, then at least you've done 90%, and the rest is really down to nature taking its course, I think.
Okay, and you're obviously responding to COVID in the way of continuing to automate and make things easier to deploy in the field. I thought it was kind of interesting how you come up with an integrated, sort of like no-touch solution, right?
Yeah, the lessons learned, I think, we had planned to deploy the Observer system in 2022.
Okay.
But on March 17th this year, we actually changed that to 2021, and it was helped by the fact that we didn't have our guys going offshore. So we actually had a lot of product focus locally in, and if anything, that focus kind of said, okay, what are the things we can change to do it faster and deliver the service in 2021? And it came down to, well, let's put it all into one housing, no cables, no wires, no calibration needed, all done and dusted, ship it out. And actually, from a business point of view, let's leave it there. And we don't even have the logistics. We can get it into, whether it's Angola or Brazil, it can stay there, and that's all done, and we'll support it remotely. So that all remains to happen, but given the learnings from previously, I think we have a really good chance of success. And for us, it's about making this available and accessible to all ORBs. So it's been interesting in the sense that in the last 6 months, I think you said it before we started recording, everything has changed. We've had to respond, but in that is the opportunity. I think that's kind of where Cathix has got to.
So I also wanted to ask about how maybe some of the other industries or sectors you work with, like the research science, have driven, the products you're offering. And I'm going to come on to Hannah in a minute, because there's lots that the research science community have done, and defence for us with as an energy industry with the autonomous machines. But I was wondering if that had also kind of come out in your work in terms of what fisheries are asking for, what those other kinds of science research guys are asking for, if it's driving us in a particular direction is helpful.
I think it's been over the years, at a board level in Cathix, even we were always conscious of being heavily oil and gas dependent. So very early on, we would have shipped systems for sustainable fisheries to the Marine Institute in Ireland. They used to pull a sled across and record video, whereas what they do now is they use our system. They can actually use machine vision on the shrimp nests. And the whole idea, it's sustainable fishery. So the objective is to count the population of shrimp. And if it's too low, then stop fishing, let it grow back up again. I think, that's one aspect. The other is deep sea mining. Like there's if we want electric cars and nickel and cobalt, mining it's a traditionally dirty industry, but if we want clean cars, we need to go and get this stuff. But we need to do it sustainably. So the best way from a Cathix perspective as well, let's record and go back to the large volumes of data that has accessible information. Know what was there before. We have to accept that there is going to be some level of mining, for example, but let's do it in a way that we can prove it and gather the evidence to show it is sustainable. So for Cathix, we see probably the next 10 years, the world wants to see this data and this evidence. And those industries, whether it's mining or whether it's defense, or well, maybe not defense so much so, but certainly all the other areas, people want to know what was it like before, what's it like now, things like carbon, CO2 storage. If we're going to store CO2, can we get a baseline before it? Can we track, is it a positive impact? Is photosynthesis happening? Are we cleaning up? Are we making it better? So there's a whole raft of applications that we see. I think the Alfred Wegener stuff, the environmental monitoring, I think anecdotally, and certainly I don't have all the evidence, but there's a lot more focus on local shallow water environmental surveys with photographic data, certainly around the coast of Ireland, I guess UK and US and Australia, I've heard about too. But building that database of evidence in a way that we can actually track our own impact at every level and stop the speculation and stop the bias. Even the researchers do good research, the industrialists want to make things happen, but there needs to be a balance, and the balance has to be evidence. And for Cathix, we're seeing a benefit from that. Certainly in let's call it the subsea sector, where high resolution data and measurement is the ultimate piece of evidence.
So I have one other question for you, which is about having some kind of common standards, and when new technologies come in, proprietary standards sometimes start, and then eventually kind of get towards open standards, and then you can go so far with a contractor and you decide you want to change, there's a way of changing, and then it's usually industries take off at that point because people have the confidence to go forward. Do you feel like we're sort of getting there now with some of the new technologies around auto venting and things like that, or we've got a little way to go yet still?
Of course, I'm going to be very biased in the answer to that and say, I think. Of
course, that's why I'm asking you, because I thought you might have a very interesting perspective about the balance between build a sustainable business and trying to grow the industry, right? There's always a balance, but
I think there's maybe to try and help with the answer. I think there is the auto for me, and I have a background 20 years in machine vision. If you go back to 1999, I think I filed a patent around machine vision for semiconductors, right? It's all public. And at that time, it was a piece of circuit board coming in from a mobile phone manufacturer on a machine. And even then, and today, it's not reliable, right? Machine vision with images is one thing. But what we've developed in Cathix is, and I think even for HANA, if you look at some of the problems with machine vision, it's the reliability of that information. The machine doesn't know how far away, how near. So when we set out on Cathix, we said, look, we want to do it fast, because if we don't reduce the boat time, nobody's going to care. If we don't, we have to fit with the workflow. So we've kind of transitioned to a point where at least now we can start talking about standardization, because there's a lot of data. But we have to fit with the way things are done. And that's always if somebody had said to us 3 years ago, forget about trying to fit with the workflow, here's the money to go and make it automated, we'd actually be done. So that's constantly the battle. And I think for new technology and as a business, and maybe that bridge is, for the business, it's easy to say, well, here's video and images underwater. Hannah talked about images above the water, and the difficulty. But just if you take that underwater, say, is that going to work under? Our view is it's not. That's why we have things like we can trigger in ultraviolet lights. We can look at fluorescence. These are in air. We did it years ago, but it's becoming of interest again because it does that thing. It differentiates in the classification process. So that's what Cathix does. But I think the bigger question on standardization, it comes down to confidence, and it comes down to evidence, and that takes time, and making sure you can still do what you need to do today. So
okay, all right, well, thanks, Adrian. I'm going to move it on so we get to hear from everyone properly. So Hannah, thank you for your talk as well. And I thought, when I was reflecting on it, about how interesting it is that all three of these talks and the different technologies they're looking at come together to come back with a kind of a new business model. I was wondering about kind of the navigation things. I saw ants on deck recently as when at one of the talks I went to, and I was really fascinated how people would be learning from animals about how to navigate boats. But I wonder if you wanted to say a little bit more about some of the use cases that maybe ASV have been applying your insights and with the machine learning. You are still on mute, so I just thought I'd tell you that as well.
Yeah, sure. So I suppose I'll talk generally about our autonomy system and the various applications beyond just machine vision. So we have our navigation system basically works on well, what we define as a risk landscape. So our collision avoidance system internally kind of develops a risk landscape, which is an internal view of what the risk is in the surrounding environment around us, and gives the autonomy system indications about areas that it should avoid and areas that are safer for it to move towards. And it also incorporates in that some COLREG information, so certain things like overtake on the right and things like that. And if you're navigating in a channel, these are the rules for giving way, and you have to give way, or you have right of way, and all that sort of thing. So we incorporate all of these kind of rules, as well as information about what's going on around us, into our system to develop a kind of a path that's the least path of resistance, if you like, the kind of the optimum solution to navigate around in the safest way. But the other thing we have to think about is making sure that the vessel behaves in a way that's predictable for a human to recognize, because typically one of the problems that we can find is that if you just leave an autonomous navigation process to itself, and you just get it to respond to what it's seeing in real time, then if you're not careful, it can end up being very jittery and kind of changing direction very frequently, and not really behaving at all how a human would, but importantly not signaling clear intent to other people on the water about where you're going. So then it makes it harder for other people to know how to respond to you. So getting the vessel to behave more like a human and getting it to understand, what is kind of acceptable human behavior, and how to give clear communications to others on the water. That's something that's really important for us to think about in our navigation. So we're using things like prediction algorithms to kind of look at the state of the environment around us immediately, but also what's it going to be like in 5 seconds time, what's it going to be like in 2 minutes time, what's it going to be like in 10 minutes time, and use all of that information to help us navigate an optimal path.
Okay, and what about when you get to a swarm? Because I know we're going to have use cases where lots of autonomous machines will, be that in some ways might be easier. I don't know, because you've got lots of data coming in from all of the actors around.
Yeah, well, actually, if you've got lots of autonomous vehicles all working together, then in theory, in some ways, that's actually easier because they're all speaking the same language. So one of the things that we're doing is we've got some research going on at the moment into developing a kind of communication protocol for autonomous vehicles to communicate with each other. So we're sort of developing this framework where they can speak in the same language effectively, and they can say, okay, right, I want to do this, but I'm restricted by the fact that I'm running out of fuel or something, or they can give each other useful communications about what they want to do, and how they can so they can understand each other's what each other's limitations are, but also what each other's intentions are, and then they can also react to that. So if there's somebody that needs help or something, they can all rally around and help each other. So yeah, so we're developing a framework and we're doing some research in that area right now.
Cool. And how close do you think we are, or are we closing in on where the navigation is becoming reliable, predictable enough that it's sort of approaching where a human is? I know there's all the sort of unusual instances where humans are much better, but for the more predictable, normal kind of operations, is the system getting close to replicating what a human's able to do for the routine, I should say, operations?
I think it depends a lot on the scenario. And I think it depends a lot on so it depends, for example, whether you're in a very cluttered environment, for example, if you're in a harbour or if you're out in open water. And also, I think one of the really big challenges with navigating on the water is that so in theory, there are all these COLREGs, but actually humans don't necessarily always abide by them. So then that makes it harder for autonomous vehicles to identify what's going on, but also to work out how to behave themselves. And you also have to kind of think about, what does human behavior really mean here? So does it mean responding to, abiding by the code regs all the time, or does it mean does it just mean being predictable? Does it just mean not crashing into stuff? What does it actually mean to be? What does it actually mean to perform like a human? I think that's a really interesting
question, isn't it?
Yeah, exactly. Yeah, and obviously computers have got very different advantages compared to humans. So we're very good at putting things into context and making decisions and justifying our decisions. Computers are very, very good at processing information really quickly, and displaying information, and processing data really, really quickly, and getting information. So I think really the where we're going is, and the optimum probably is going to be having the two working together, but working together in an optimal way. So we could have a situation where the system's giving alerts, but things that the human might not notice, or picking things up ahead of time that the human might not be able to, that a human might not necessarily recognize as quickly. And as I said before, bringing together, or doing the sensor fusion to bring together all the data from disparate sources and things, building up one big picture, so the human can just focus on that one picture. But the human is probably always going to be better at the actual decision making and the justification, and ethically, in many cases it is desirable for the human to really be making the decision rather than the machine.
So what you describe is covered somewhat in this book by Accenture, called Human Plus Machine. And one of the things they talk about is having, like, we have a human resources department, we have like a machine resources department. So as we become more reliant on algorithms, we need to do a better job, or a more serious job about managing them. So I don't know if you have seen any of that come through now, where there starts to be corporate systems to look after algorithms.
Well, yeah, I mean, and this is the thing, this is the really interesting thing about where the industry is going. I think there's going to have to be a big change in what users' expectations are of the systems, and their expectations of themselves, to their responsibilities towards the system themselves. Because, I mean, like I was saying at the start, you have to provide lots of variety of all the scenarios for your machine to really learn. And the only way to do that really is to be constantly teaching it. So when you're out and about, you have to be providing feedback to the machine constantly and telling it, yes, you got this right, no, you got that wrong. And that's the only way it's going to get better. So to really use this stuff in anger and to get it to a point of being really reliable, that's what we're going to have to do. So I think people's expectations are going to have to change, and their expectations of themselves, of their responsibility towards the system, I think is going to have to change.
All right, that's good. I think we're nearly out of time. So, are there any final comments that you would like to make? Any of you? So, Hannah, any final thoughts you wanted to share with the audience?
Yeah, I think yeah. Well, I suppose the other thing I would say is that so I mentioned how the users have I think users have a lot of expectations of the system. I think because of the way technology has evolved, and has evolved so rapidly recently, particularly with like machine vision applications. People have facial recognition on their phones and things. People kind of have the same expectations of image recognition in autonomy. But the problem is the image recognition in an autonomous situation, autonomous vehicle scenario, is much more complicated than facial recognition on a phone. And so I think we're kind of at we're sort of in at the peak of a Gartner's hype cycle at the moment, where there's a lot of excitement about what could be, but there's still a lot more research that needs to be done to get us to a point where where we're really safe and things could be reliable. And I think there's going to have to be some patience and a lot of trialing, a lot of working things out. So yeah, I think we're in very exciting times, but we we've also got a lot of work ahead of us.
Sounds good. Any final comment from you, Felix? Thank you, Hal.
Well, commenting on the perspective, in the simulators and in the remote collaboration and training scenarios, it's also, I think it's at the moment when now everyone is aware that those technologies are out there. Not everyone is aware how useful they might be to the training and operational scenarios. So there are early adopters, but we also see that the current circumstance and a certain restriction on travel will accelerate the development of remote involvement, remote training, remote operations. So that's something that we can also welcome.
Yeah, that seems likely to happen. Adrian, do you have a final comment? Thank you, Felix. Oh, you're still on mute, Adrian, sorry.
Do it again. I think I'll just leave it with the parting comment is maybe make haste slowly. So it's I think it's the reality. We have a good idea where we want to get to. We want to get there quickly, but the practicals say that, well, we're going to need to give it more time. And maybe the expression is the human learning has to be right before the machine learning is right.
Okay, that's a good thought. All right, well, listen, thank you, everyone. I really appreciate your time today and look forward to working again soon. Cheers. Bye.
Thank you. Bye-bye.